people missing.
For posterity.
Yes.
Oh, so when I'm.
So, I never know when you're going to be gone.
Excuse.
Yesterday we were talking about the relationships between displacement versus time graph, velocity versus time graph, and acceleration versus time graph. And what did we say? How can we go from a displacement versus time to velocity versus time? What characteristic?
The slope equals the velocity.
Right. The slope. The slope of a displacement graph equals velocity. What about if we have that velocity versus time graph? What about that tells us the acceleration? Slope again. And then just as a little intro to what you're going to see in calculus and how calculus can be useful here, if we have something that is, say, as an example, quadratic formula, so that means proportional to x squared, so some numbers with x squared, what would that make our velocity look like? What happened to this kind of function when we find the slope? It's using a derivative, but essentially finding the slope. It goes to linear. We decrement this exponent by 1. So this would be proportional to x. Okay, and we do the same thing when we find the slope of the next one. This is essentially x to the 1, so it becomes x to the 0. That means this would be a constant. Could even be 0, but it's a constant number. Let's take a practice one. Let's have that's okay, you can just sit down. Let's take our displacement versus time. And velocity versus time, and an acceleration versus time, and see how that translates. So I'm going to make, I'll do a simple one first. Let's have a straight line for our displacement. And you got some of these to match. You would have been walking away from the wall. You wouldn't have been changing speeds. That's very similar. What we want to do to find the velocity is sketch out the slope. Now, when we're doing this, we are not going to do too many with actual numbers. So these will be sketches rather than exact. You certainly could, if you've got all this marked out, you could find the numeric slope, use that for velocity and so forth. But for our purposes, we're just going to sketch them. So, what does the slope of this look like?
It'll be a flat line.
Okay, flat line.
And it'll be above the T.
Yep, above the axis. It's a positive slope, and it's straight, so it's a positive constant. So our velocity would be a positive constant, which we kind of knew already. That's a steady speed, right? And that's what this says. Okay, now going over to acceleration, we need to take the slope of velocity. What's the slope of this velocity graph look like? Well, 0. It's 0. It's flat. 0 slope. So acceleration, I'll put it right above the 0, is 0. Like that. Easy peasy. Yep.
Are you just putting it above the 0 so we can see it?
Just so you can see it. Yeah. It'd be right on the 0. So here we have a linear. This would be of the form x to the 1, a constant x to the 0. Now if this is a constant, it's already, so some number, we'll call it m times x to the 0. If we take the derivative of that, we bring the 0 down and multiply it through.
Fire, fire. Please institute evacuation procedures. Fire, fire. Please institute evacuation.
As I was saying, we started out with a linear, which is x to the first power, constant, which is x to the first, or x to the 0th power, and then on this branch, since the derivative would actually be just 0. So let's take another example, a little bit more challenging one. You'll probably see, well, we'll use one that we talked about yesterday. Curve like that, displacement. This is like a parabola, even though I can't probably draw it just like a parabola. But if you think of that, and think of that as proportional to x squared, it can help you with the next steps. You can also just think of it as if you took a tangent line to various parts, what would the slope of that tangent line be? So if we start out here, what does a tangent look like? Basically flat, which means a slope of what? 0. So that means our velocity must start out at 0. As I'm going up, what's happening to my slope? Getting steeper, it's getting higher. So that means my velocity is getting higher. Now that still doesn't really tell us the shape, but it does tell us it's making kind of that way. If we use the derivative type part of this, we have a quadratic here, so we'd have a linear function here. So that indicates that it is aligned. Okay, well now this looks just like our last displacement. We're finding the slope of it to get acceleration, and we said that that was a positive constant. Same deal. Like so. So going this way, going from a displacement or to the right, or from a velocity to the right, is just takes a little practice. It's not that bad. Any questions on the slopes that we've been talking about here before we move on? Okay. There is more we can use these graphs for. So let's take a look at that. We're going to do a little bit larger for illustration. We're going to look first here at a velocity versus time graph. We're going to start out with a fairly simple part of this. Let's say that that's flat. And it goes from some time 0 to some time t, which we're just going to call t, and it goes from a 0 velocity up to some velocity v. We could call this like t final, v final, if you wish. If we want to find how far something travels when it's got a constant velocity, we did that with the last homework. We said, well, the definition of a velocity is a change in position, so it's displacement over time. And if I want that change in position, I can just multiply both sides by t. And I can get my displacement by multiplying my constant velocity by the time elapsed. Well, what happens if I multiply my constant velocity here by the amount of time elapsed? What do I get that's as it relates to my graph? What does that tell me about my graph that I've drawn? Well, it wouldn't be equal to it unless time, I mean, the numeric value might have time equals 1 second, but it wouldn't be equal to it. No, I'm multiplying the height from here to here by the width from here to there. It's area. It's in fact the area of this. That is another way we can use these. The area under a velocity versus time graph is the displacement. This is actually the opposite rule for the derivative rule. This in calculus is called an integral, which is just summing up the area under a curve. So these two things are similar. Now, if you get another part of it going down here, under the curve then it really means from your line to 0. So if you're this would be a positive displacement, delta x greater than 0. This would be a negative displacement, delta x less than 0. If you were looking from time 0 way out to this time, whatever it was, you would find these two separately and then just add them, one positive, one negative. It looks like it'd still be overall a positive amount of displacement. Let's also then, before we finish, look at...
Would that mean that the area on an acceleration plot, acceleration by time would be the velocity?
That's what we're going to see next. So let's pick a simple constant acceleration. We go up to some, I'll call it A1 here, value A1, T1. And we know from our reading and from our practice that acceleration is equal to a change in velocity over a change in time. And if we want a change in velocity, we multiply both sides by t. And yes, same thing. So we're multiplying the acceleration here by the time. And that tells us the area underneath this. This, by the way, I set up with constant velocity on the last one, constant acceleration here. Doesn't really matter. If we go at some angle, it's still, here's our area for this section. We'd want to find the area for here. Just remember that if this is, say, a negative a, this would be a negative amount. You use the height based on what the height is here. And you do 1/2 height, base times height. Okay. So we can go back and forth fairly straightforwardly on this. This can also be useful when you maybe have information about an acceleration and you just want to sketch and see what would it look like, what would the velocity look like. You can always look at this and say, okay, the velocity is going to be the area under here, so what's happening with it? Let's practice one of them and then we'll have some work time. So let's say instead of starting with a displacement like we did at the first part, we start with an acceleration, and then I want you to find the velocity and then the displacement. So here we have acceleration in time, velocity in time, and displacement in time. Let's do something tricky. Let's again assume that's a straight line. And now I want to say, okay, what can I learn from this graph with this acceleration that will tell me about velocity and, I think that's crooked, but that's okay, and displacement of it. We do lose some information when we do this. We can't tell everything based on our sketch without numbers, but we can do quite a bit. The way I think of this, certainly we can translate this and say the area underneath this curve tells me what's happening to velocity. So if we go from time 0 to a little bit of time, there's quite a bit of area underneath that slice. So that means there'd be quite a large change in velocity. We take the next one, the area under that slice would be a little bit smaller, so the change in velocity is less. And we could keep going like that. I find it a little easier to look at it piece by piece, but slightly differently and say, okay, this acceleration right there is the slope of my velocity plot. So let's say, what can I say about the acceleration right there? Well, it's positive, right? So that means my slope from a velocity right around time zero must have been positive. And it's pretty high. So my slope must have been a high positive value. What does a high positive slope look like? Almost vertical anyway. Yeah, probably pretty steep. Positive meaning going up from left to right. So at least for a little while, my slope was high and positive. What about here? Is it still positive? Is it still as high? It's not. It's not real low, it's sort of a medium. So midway through this time, I know I'm going to be going up this way, but by midway through, my slope has changed, and it's sort of a medium slope, still positive. What about right here? What's the value of acceleration right there? 0. So that means my slope over here must have been 0 at that point. What does a 0 slope look like? Sort of flat line. Now these are still going to interconnect, so I wouldn't put my 0 slope down here. There's no negative slope part of this to connect them. But then I can go through and say, oh, it must be about like this. Now let's look at this. This is a linear, right? Sorry, go ahead, Alex.
I thought the tangent line, though, like the slope of the tangent line equals like the acceleration.
Uh-huh.
It doesn't look like the slope of the tangent line.
What's the slope right there?
That'd be like,
Positive and pretty high, right?
yeah.
Isn't that what acceleration is right there?
Okay.
And then here, it's positive, but it's sort of a medium. Certainly lower than it had been. So that's the part of the line right there. And then here, the slope is 0, which is what acceleration is. Going this way is it is more challenging to wrap your head around. So if you look back at it, then you can kind of double check if you're doing that part okay. The other thing to remember is, as we are going from displacement to velocity to acceleration, we were losing one exponent in our description. Well, what's the formula for this going to look like?
X third.
It's x. It's a negative something times x, but it's x to the first power because it's linear. Well, this one had one higher. So it must be x squared. What's the next one going to look like? Should be x cubed, yeah. Because if we are going the other way, we take 1 off of it each time. If we're going from acceleration to velocity to displacement, we have to add 1. This gets tricky now. We're going to use the same sort of technique going from velocity to displacement as we did over here. So let's look at an individual point. Velocity there. What does it look like? It's low. We can be even more specific. It's 0 the way I drew it. That means the slope must have been 0. Now the part that we lose here is, I actually don't know where vertically this is. And in fact, the curve I drew could have just as well been down there. I kind of started it arbitrarily at 0. Don't have to. We lose that information, and it's still correct based on the information we know. But right here, our velocity is 0. So I'm going to have a slope of 0. I'll put it up here. I could put it down here or down here, and it'd still be okay. If I look at this point, tell me about the velocity. Is the velocity positive here? Yes. So that means over there I had a positive slope. Is it high, medium, or low value? Kind of a medium. It's not the highest it'll get. So my slope over on my displacement was positive and medium in slope. So I should have started lower, it doesn't matter. This is okay as well. But that part of my line must have had a positive slope. That's sort of a medium. What about my value of velocity here? It's at its maximum. Is it positive? Yep, it's a positive velocity. The value of the velocity is higher than any point before it. So my slope over here must be positive and higher than any point from before it. And you're thinking, that doesn't look like an x cubed. Yeah, right. If we move this up or down, we'd get a little bit different view, but also, yeah, the part that we don't see could go like that. And there, that's why it's an x cubed. So it's a similar shape to a parabola, but would technically be slightly different. This will be fun, don't worry. Homework 2.1 has you practicing all of these different parts. It's two-sided, Shai. Front side gives you some motions. It either gives you displacement, velocity, or acceleration. It asks you to fill out the other two of those that it doesn't give, and then to describe in words how you would move relative to a wall with a motion detector in order to match it. So what you should do before you describe it is find the displacement versus time graph first. That's going to be the easiest one to describe your motion on, and then go and describe it. The back is a numerical part that is practicing this stuff right up here with the area underneath and numerical slopes and that sort of thing. What can you tell from a numerical graph?